everyone, and welcome to today's lecture. We'll be covering Chapter 5, Data Flow Architectures. Data flow architectures are a class of software design models that are primarily concerned with how data flows through a system. In these architectures, the movement of data drives the execution of system components. These models are particularly useful for applications that need to process streams of data in real time or perform transformations on data as it passes through various stages. Today, we'll focus on one specific type of data flow architecture called the pipe and filter architecture. This architecture provides a modular approach where data processing is broken down into a series of transformations, making it flexible, reusable, and highly efficient for a wide variety of applications. Let's start by defining the pipe and filter architecture. This architecture is essentially a type of data flow architecture, where the system is decomposed into independent components called filters. Each filter processes data and then passes it on to the next filter through pipes, which act as conduits for the data streams. The key idea here is that each filter is responsible for a specific transformation or operation on the data, allowing the system to be broken into well-defined, reusable components. In this model, there are several major elements. Data source, this is where the data originates. Filters, these are the processing units that transform data. Pipes, these serve as the connectors between filters, allowing data to flow from one filter to another. Data sink, this is the final destination where the processed data is stored or output. The pipe and filter architecture supports concurrent and incremental execution. This means that each filter can process data as soon as it arrives, without waiting for the entire data set to be available. This incremental nature is especially useful in distributed systems, where data processing can be parallelized across multiple components. Now, let's dive deeper into the core components, filters, and pipes. A filter is an independent modular component responsible for transforming the data. Think of a filter as a small self-contained unit that takes input data, performs some kind of operation on it, like converting text to uppercase or filtering out unwanted elements, and then sends the processed data forward. One of the key characteristics of a filter is its independence. Filters don't need to know where their data comes from or where it's going. This independence makes them reusable in different contexts and allows you to add or remove filters from the system without much difficulty. A pipe serves as the channel through which data flows from one filter to another. Pipes can carry different types of data, including binary streams such as files or images, character streams like text data, structured data like XML or JSON objects. Since each filter processes the data locally and independently, the filters can be executed in parallel threads, which makes the system highly efficient. For instance, in Java YO streams, pipes are used to connect input and output streams for reading and writing data, enabling multi-threaded concurrent operations. There are three primary ways in which data flows through filters in this architecture. 1. Push-only, write-only. In this method, the data source pushes data downstream to the filters, which then transform and push the data to the next filter or data sink. This is a unidirectional flow where data is always moving forward. 2. Pull-only, read-only. In this method, the data sink or downstream filters pull data from the upstream filters or data source. This is the reverse of the push method, where components only request data when they are ready to process it. 3. Push, pull, read, write. This is the most flexible method, where filters can both pull data from upstream components and push transform data downstream. This approach allows for more adaptive data processing, depending on the system's needs. The flexibility of using different data flow methods means that we can tailor the system to the specific processing requirements. For example, a real-time system might benefit from a push-only model, while a batch processing system may favor a pull-only approach. Now let's explore the two main types of filters. Active filter. An active filter is one that actively pulls data from the upstream source and pushes it downstream after processing. These filters work well when paired with passive. Pipes. An example of an active filter can be found in Unix systems, where data is pulled from one command and pushed to another in a pipeline. Passive filter. A passive filter, on the other hand, does not actively pull or push data. Instead, it relies on active pipes to feed data into it or pull data out of it. The filter itself performs the processing, but it depends on external mechanisms for the flow of data. In Java, for example, PipeWriter and PipeDriver classes are used to handle synchronization between active and passive filters. These filters can be used in a variety of scenarios, depending on whether the system needs active data fetching or passive data processing. To understand how the pipe and filter architecture works in practice, let's look at the class and sequence diagrams. In the class diagram, we have several components: the data source, filters, pipes, and the data sink. The data source provides the initial input, and the filters process the data step by step. The pipes handle the transport of data between filters. Notice that these components interact with each other in a very modular fashion, with clearly defined roles for each component. The sequence diagram shows how these components interact in real time. Here's how it works. Filter 1 reads data from the data source, processes it, and passes it through the pipe. Filter 2 then picks up the data from the pipe, processes it again, and sends it to the data sink. This sequence illustrates the smooth flow of data from start to finish, with each filter performing its task independently. To further illustrate the pipe and filter architecture, let's look at a more detailed real-world example. Imagine a series of filters where the first one, called the conversion filter, converts all lowercase characters to uppercase. This filter processes the data incrementally, meaning that as soon as it receives part of the input data, it begins the conversion process without waiting for the entire data stream. The next filter, the matching filter, selects specific characters, let's say A and E, from the uppercase data stream. This filter also works incrementally and starts processing data as soon as it receives it from the conversion filter. Finally, a sort and count filter counts the occurrences of A and E and sorts them alphabetically. However, this filter needs to wait until it has received all the input data before it can output the final results. This pipeline demonstrates how filters can work concurrently to process data as it moves through the system. In pipe and filter architectures, reading operations can be either blocking or non-blocking. A non-blocking read means that the filter reads data as soon as it becomes available. The system doesn't halt. The filter continuously processes any data that comes through the pipe. This is common in real-time applications where performance is critical. A blocking read, on the other hand, pauses the process until new data arrives. This can be useful in systems where it's necessary to wait for a complete data set before proceeding with further processing. In this diagram, we see that filter 1 performs non-blocking reads, while filter 2 performs blocking reads, showing the difference in how data is handled based on the system's needs. Unix systems are a perfect example of the pipe and filter architecture in action. The Unix pipe operator allows you to connect the output of one command to the input of another. This setup enables the sequential execution of commands, where each command processes the data and passes it along to the next. A common example is who WCL. In this case, the WHO command lists all users currently logged onto the system. The WCL command counts the number of lines, which corresponds to the number of users. The beauty of this architecture is that WC can start processing the data before who has finished outputting all of its data, illustrating real-time data handling and the efficiency of the pipe and filter approach. Let's break down this more complex example of a Unix pipe and filter system. The cat command reads data from an input file and passes it to the T command, which splits the data stream into two paths, pipe and pipeb. The data in pipe is filtered using the grep command to find occurrences of the character A, while the data in pipeb is filtered for the character C. These separate filtered data streams are recombined with the cat command and passed to a final filter, unique, which counts the unique characters. This demonstrates how Unix leverages the pipe and filter architecture to handle parallel data processing across multiple components. The pipe and filter architecture excels in domains that require incremental processing. It's particularly useful when you can break data processing down into a series of manageable, independent steps. Incremental processing, systems where data can be processed step by step as it arrives. Simple, stable data formats. This architecture works best when data formats are straightforward and consistent, such as plain text or simple binary formats. Performance gains, it's ideal in situations where pipelining can improve performance by allowing multiple components to work simultaneously. Producer-consumer problems. The architecture is also useful for solving producer-consumer problems, where one component produces data and another consumes it. Let's summarize the main benefits of the pipe and filter architecture. Concurrency, filters can be run concurrently, greatly improving throughput. Each filter processes data independently, allowing multiple stages of the pipeline to operate simultaneously. Reusability, filters are modular and reusable. You can use the same filter in different contexts or systems, saving development time. Modifiability. The low coupling between filters makes the system easy to modify. You can add, remove, or replace filters without disrupting the overall system. Simplicity. The architecture ensures a clear separation of concerns, with each filter having a well-defined responsibility. Flexibility. Supports both sequential and parallel processing, making it adaptable to a wide range of use cases. Of course, there are some limitations to consider. Dynamic interactions. Pipe and filter is not well suited for systems that require dynamic back and forth interactions between components. Data format restrictions. The architecture assumes a simple, stable data format, such as ASCII or binary streams, which may not be suitable for more complex data types like XML or JSON. Transformation overhead. Each filter may need to repeatedly parse and transform data, adding overhead to the system. Configuration challenges. Dynamically configuring a pipe and filter system can be difficult, as it's not designed to handle rapid changes in system behavior. That's a wrap for today's lecture. We've covered the pipe and filter architecture, a powerful tool for managing data flow in software systems. This architecture allows for modular concurrent processing and is particularly effective in distributed systems and real-time applications. However, it's important to be mindful of its limitations, especially when dealing with complex data formats or dynamic interactions. I encourage you to think about how this architecture might be applied in your own projects or real-world systems. If you have any questions or need further clarification, feel free to reach out. Thank you, and see you next time.